So we just did 15. I think 17 was the next one that had a lot of questions. So let's do that and then maybe see if people have questions on the 15.2 stuff.
Yeah.
Is that cool? Okay. 17. All right, so here we go. 15.1, number 17 says, in the figure at the right, a block weighing 14 newtons, which can slide without friction on an incline angled at 40 degrees, is connected to the top of the incline by a massless spring of unstretched length. Let's just call that L. Unstretched length of 0.45 meters and a spring constant of 120 newtons per meter. Oh, right. How far from the top of the incline is the block's equilibrium point? Okay. So, and then your drawing looks like this. You've got a ramp, inclined at 40 degrees, a little thing, and a little thing, and here's the block. All right, and so we want to know how far from where it is right now is, what does it want, the spring's equilibrium point? No, wait. Oh, I gotcha. I gotcha. Okay. I understand. All right, so, yeah, some of this is just understanding what's going on in the equation, in the problem, right? So let's do this. We're trying to find the block's equilibrium point. So what do we mean when we say the block's equilibrium point? Sure, yeah. Sort of. So what would that accomplish? It would keep the block in place. We need to find the point where our net force is 0, right? Good? All right. So here's the deal. So before we have the block attached, our spring looks like this, right? So that this is a distance of L, right? An unstretched length of 0.45 meters, right? Then we attach the block, and now it's stretched some new distance, which I'm going to call L plus X. Why did I choose X? Just F equals Kx, right? Okay, so at this instant, there are two forces acting on the block. There's the force of the spring, which is equal to Kx, and what other force? Yes, gravity. Point for me. We need the parallel component, right? Follow? Okay, so FG parallel, use a sine or cosine? Sine, right? All right, so here's my equation. I need FG parallel equal to the force of the spring. So FG times the sine of 40. So I guess I can just plug in my FG, right? Fix that eraser. It's too big. Ah! Uh-oh, what happened? Did I miss something? So 14 times the sine of 40 is equal to K times X, right? Is that better?
Yeah.
Yeah. Oh, you're okay. I'm sorry. I'm always standing right in front of it. I need to rearrange my desks. All right. Is everybody good up to here?
Yeah.
All right. So solve for X. 14 sine 40 divided by 120. And your X ends up being 0.075. So that means that my equilibrium point is 0.45 plus that, right? So what is that, 0.525? Good or no? Cool. All right. So then it says if the block is pulled slightly down the incline and released, what's the period of the resulting oscillations? So here's the deal, you guys, and this is the main reason I assigned this. It turns out we know what our spring constant is, right? It turns out, even though it's still an inclined plane, you can still use T equals 2 pi root m over k, and it still works just fine.
That is cool.
Okay? Now, the algebra behind why that works is a little bit complicated. We could do it if we had a little bit more time. I'm not going to, but it does work. Okay? So, you know your force of gravity, so find the mass. You know k because it was given to you. Plug your numbers in, you're done. Cool? So that problem seemed like, I looked at it and I was like, oh my god, inclined plane, this is going to be a pain in the ass. But it ends up actually not being that bad. All right, so make a mental note of this, that this works even on an inclined plane. Yes, sir?
This is just a concept question. Because one of the forces acting on the box is gravity, would eventually stop oscillating?
Theoretically, no, because you're still conserving energy. You're converting between elastic potential energy, gravitational potential energy, kinetic energy, and just sort of oscillating between those three forms of energy. But the total should always stay the same. Okay? Now, in reality, yes, it would eventually stop because of friction. Even if there isn't friction, the spring is going to get hot from deforming the spring. So you get thermal energy, heat energy. All right, good. Jacob, and then Anthony?
Should we have to add the length of the spring or no? Is this from like the top of the...
For what? For part A?
Yeah.
Yeah, I said that. I didn't write it down, but yeah. Yeah, so you're right. So for part A, the answer would be 0.075 plus 0.45, which is what, 0.525? Yeah. Anthony?
That's fine.
Same thing? Okay, cool. Sorry, I should have written it up. All right, good, you guys? Okay, cool. All right, so let's take a look at the 15.2 stuff. There are only 8 problems there, and there were some multiple choicey things. I feel like I don't know. What do you guys want to do? How'd the problems go? Number 8?
Yeah, no.
7 and 8.
That's the only one that
Okay. Yep. Oh, am I still recording here?